All right, this video is the third of the kinematic equations. And as we move into the third and fourth, things will get a little bit more complicated. The way that they're derived and the types of units and the unit cancellation that's involved with them gets a bit more complicated as well. The third kinematic equation starts with a velocity time graph. In our first unit on describing motion, we learned how to look at one of these velocity time graphs and calculate the acceleration of the object using the slope of the line, rise of a runner, delta V over delta T. We also learned that a straight line on one of these graphs indicates constant acceleration. We learned that a line going up means it's positive acceleration, as in the object is speeding up. And a line going down means negative acceleration, as in an object slowing down. Today, what we're going to do is look at where displacement is on this particular graph. On a velocity time graph, displacement, or delta x, is equal to the area under the line. So if we calculate that area is going to be equal to the displacement, or delta x, for our object. The problem is this is an irregular shape, and there's no simple, easy formula that we can use to calculate what that area is. So what we have to do instead is divide this up into two easily usable regular shapes. We divide this area up into a triangle and a rectangle. So if we figure out the area of that rectangle and the area of this triangle and add the two together, we would have the displacement of our object, or delta x. For the rectangle part, the area is the length times the width. So VI times T. For the triangle, the area of the triangle will be 1/2 base times height. The base of my triangle is T. The height of my triangle is VF minus VI. And that would be a perfectly legitimate, perfectly valid way to calculate that area. And we could leave it at that, and we could do calculations with this. But in the end, what you're going to find out is that the goal of each of these kinematic equations is to eliminate one variable from a set of five. Five variables that we work with are VF, VI, A, T, and delta x. Each equation takes one of them out of the mix so we can work with the other four. In this particular equation, what our goal is going to be to do is to get rid of VF. Ultimately, that is what we're trying to do. So to get rid of VF, what we're going to do is we're going to turn to the acceleration equation. Our acceleration equals delta V over delta T. And break down that velocity into VF minus VI. Then rearrange that equation so it says VF minus VI equals. So to isolate VF and VI, since we're dividing by delta T, we'll do the opposite operation and multiply both sides by delta T. Rearranging this so it says VF minus VI equals, we get A times delta T, or A times T. What we're going to do is we're going to take that expression right there and replace the VF minus VI with it. If VF minus VI equals A times T, we can take that out and replace it with a times t. Now we don't want to leave it as this because this can be simplified. 1/2 t times a times t. T times t would be t squared. So what we end up doing to wrap this all up is that little simplification. Writing this equation as delta x equals the rectangle part, vi times t, plus our new triangle part, 1/2 a t squared. So that is our third kinematic equation and where it comes from. And basically what that equation does is calculate the area under this line. And the area under this line is equal to the displacement of our object. Again, it removes VF from the equation. If you look at the other equations that we've done, VF has been a part of them. This one allows us to do some work, predict some situations and scenarios where we don't know what VF really is. So let's take a look at an example. All right, so a car accelerates at a rate of 2 meters per second squared for 3.9 seconds. If the initial velocity is 12 meters per second, what distance will it travel as it accelerates? Again, we can use the words velocity and speed interchangeably in this because this is linear motion. And the signs will take care of the directional components for us in our velocities. That's positive 12, so we can interpret that as 12 to the right. And we can use distance and displacement interchangeably in this one because this is linear motion and we are moving in a single direction in this case. First thing we want to do, as we always do, is try to figure out what all these numbers are. I can look at that and see meters per second squared and know that that's an acceleration unit because of the squared time. But it also says accelerates at 2 meters per second squared. I've got 3.9 seconds. Seconds measure time. And again, there's nothing else with it. It's just seconds, so it has to be time. And I have 12 meters per second. Meters per second. Without the squared unit, we know that's a velocity or speed, and it tells us specifically its initial velocity. Once we've identified all of our numbers, we have to think about any hidden or assumed numbers that we might have in our question. Hidden or assumed numbers include velocities of 0. We have those whenever we're going to a stop or at rest or starting a race, something like that that implies that we're not moving at some point in time. This question doesn't say anything like that. There's no stopping or at a standstill or at rest or anything like that. And then the other big assumed number would be acceleration due to gravity, the 9.81 meters per second squared. That deals with falling objects or objects that have been thrown straight up in the air. And again, our question doesn't say anything about those. So we don't have any hidden or assumed numbers in this. We do need to figure out what we need to find. We want to know what distance, again, using distance and displacement interchangeably in this one because it is linear motion and they are the same. We're looking for delta x. Now, when we get to the mixed sets, when we're working on multiple equations at the same time, this is the point where you would look at what you have, a, t, vi, and delta x, and find an equation, or at least try to find an equation that has those four things in it. And that would be the equation you'd want to use. We're only working with this one equation right now, so we know that's the equation. But again, when it comes time to do the mixed sets in a few days, it's a matter of looking at what's here and figuring out what equation fits that set of variables. So let's go ahead and sub everything out. Delta x, that's what we're trying to find. Vi is next. Vi is 12 meters per second. Times t, the time is 3.9 seconds. Plus 1/2. A is 2 meters per second squared. And then our time is 3.9 seconds again. This time we're going to square it. I was asked the other day in class, is there an order of operation thing here with all these parentheses and stuff? I'm just not using multiplication signs. And because I'm not using multiplication signs, another way to express multiplication is to put numbers in parentheses. So where we see this, that just means 12 times 3.9. Or we see this, it's 1/2 times 2 times 3.9. And that's the first thing I'm going to do. I'm going to simplify my equation before I do my addition. I'm going to go ahead and take care of all this multiplication first. And while we do that, let me take a moment to mention something about unit cancellation. My first expression is 12 times 3.9. 12 times 3.9 is 46.8. I have seconds in the numerator, I have seconds in the denominator, so those seconds will cancel out, leaving me with nothing but meters. Over here, it's 1/2 times 2 times 3.9. That's 3.9. For unit cancellation here, I have second squares in the denominator. I'm going, oops, realized I didn't square my 3.9. 3.9 squared times 2 times 1/2 is 15.21. When I square this, I end up with second squared in the numerator and second squared in the denominator. So again, that time is going to cancel out and I'll be left with nothing but meters. As far as unit cancellation is concerned in this, the goal is to have nothing but meters or miles or feet, whatever it is, to have these two things be nothing but the same distance unit. So when we add them together, that's what we get for delta x. In order for that to happen, all of these times have to be the same. So my acceleration's in seconds squared, my time is in seconds, my initial velocity, the time unit is seconds. I need all of those to be the same. That way all this unit cancellation will take place like it's supposed to. The seconds here can cancel the seconds in the velocity, and then the second squared can cancel the second squared in my acceleration. All those time units have to be the same, seconds, 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 so the unit cancellation can occur. If they're not all the same, then your unit cancellation won't work out somewhere, and you won't have a correct unit for your answer. So adding these two together is 62.01. Again, we're not using significant figures. It's a lot to think about when you're still trying to learn a process, trying to keep units straight and things like that. So I don't use significant figures when I'm doing these kind of problems. When we round wherever. I can tell when you round, I can tell when you haven't. So you can do 62 if you wanted to for your answer, or 62.01 if you want to write down everything. It's up to you. That's a pretty straightforward one. Again, everything was the way it needed to be. All my units were the way they needed to be. I didn't have to do any unit conversions before I did my calculation. There's no algebra to do here. It's just probably the simplest way we could use this equation. So let's go ahead and make it a little bit more complicated. All right, so we have a rocket accelerating at a rate of 3.7 miles per hour per second for 2.2 minutes. If its initial velocity is 70 miles per hour, how far will it travel as it accelerates? Again, first step in the problem solving process is to figure out what all these numbers are. Miles per hour per second, 2 time units in it, says acceleration of, that's A. .2 minutes, that's a time. Then we have an initial velocity of 70 miles per hour. Once we've taken care of all of our numbers, we think about any hidden numbers that we need. This is a rocket, and we can probably assume it's going to go up. But we're not going to use the 9.8 meters per second squared here because we already have an acceleration at 3.7 miles per hour per second. It also doesn't say anything about at rest or stop, so we know we don't have another velocity in there of 0. So no hidden numbers. And then look for what we're trying to find. How far that's delta x. I'll take a look at the units that we have. Seconds, minutes, hours. We have a mix of units, so we can't have that. They all have to be the same. And they could all be seconds, they could all be minutes, they could all be hours. It really wouldn't matter. You're going to get the same answer either way. What I'm going to do is convert these all to hours because, I don't know, I think to me anyways, that seems the logical thing to do. We won't have to do anything with our velocity. It'll just stay 70 miles per hour. We will have to convert our minutes into hours, and that's pretty straightforward. We just divide by 60 since there's 60 minutes in an hour. So this is going to convert to 0.043 repeating. I'm just going to round it to 0.043. And then we're going to convert the miles per hour per second into hours. If it goes 3.7 miles per hour faster every second, multiply that 3.7 by 60, 222, that would tell you how many miles per hour faster it will go in a minute. And then multiply it by 60 again, and that would tell you how many miles per hour faster it would go if it accelerated for an entire hour. And that is 13,320 miles per hour squared. Big number, but it is a big unit. Again, what that number is telling us is how much faster it would go if it were allowed to accelerate for an entire hour. Now, just pay close attention to this. Miles per hour per second. That is a valid acceleration unit. But whenever we're using this equation here, we have to have one of these squared acceleration units. And the reason for that is just making sure that all my time units are the same. When we put our time in here, it's going to be squared. So we're going to end up with a squared time unit for t. We need to make sure we have a squared time unit for a so that they'll cancel out correctly. At this point, now that we've done all the conversions, we can substitute and solve. Delta x equals vi times t, 70 miles per hour, times 0.043 hours, plus 1/2 a, 13,320 miles per hour squared, times t, 0.043 squared. Again, it's all got to be the same, hours, 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 so we get the correct unit cancellation in our problem. Then we're going to do the multiplication first. So 70 times 0.0, what's the 0 for that? 43. It's 3.01. And what happens is the hours cancel and all we're left with is miles. Plus 1/2 13,320 times 0.043 squared. So 0.043 squared, I always do that first. And as I said before, because I don't trust calculators, 13320 equals times 0.5 equals 12.31434. That's the whole thing the calculator says. Again, you could just round that wherever you want to. That's hours squared. This is going to be hours squared, so those cancel, leaving us with nothing but miles. That's our goal. Get those two distance units to be the only units left, making sure they're the same units. Add my two numbers together. The rocket would travel 15.32 miles as it accelerated. Again, make sure all those time units are the same. That's really important in this, so we get the right unit cancellation. The distance units have to be the same as well. If this is miles per hour, that has to be miles per hour. If this were feet per second, then we're really messed up. We got to convert not only the hours into second, or the seconds into hours, we have to convert the feet into miles. We have a lot of work to do converting that. But again, make sure the units cancel. That's the bottom line. And I know a lot of students don't like writing down their units when they do their math, but the older I get, the more I realize why it's so important. It really guides you through it and makes sure that you've set everything up correctly and are doing everything correctly. At this point, I'm going to assume you can do the algebra. The unit conversion stuff is the hardest part of this. I'm assuming you can solve this for VI or A. And those are the only two that I would solve for in this equation. I wouldn't even try to solve this for T. If I were looking for time, I'd use one of the other kinematic equations. I would even resort to a two-step process before I dealt with T and T squared in the same equation. So I would not use this one to solve for T. But I can assume at this point that you could solve this for VI if you had to. You could solve this for A if you had to. One more kinematic to go.